My presentation is about a research paper on an information transfer technique called memory stone, which is used to transfer information across multiple devices. I would like to discuss about the concept of memory stones, what are the client and server-side applications used here, how they work, what are the supported platforms, and the areas of improvement. So the concept behind this memory stone is drag and drop. Like we all know, in a conventional drag and drop operation, we just drag an object in a device and will choose a place where to drop the object. Similarly, the memory stone is a technique which helps to perform the same action but across multiple devices. Like we can choose an object in one device, I can drop it in another one. To picturize it, like here we can see a user is picking up the data, is carrying it and dropping it on a target device. A visual feedback is given here in the form of a stone. That's a virtual stone. This visual feedback will help to reinforce the metaphor of carrying something tangible from one device to another. So what's happening is the memory stone technique is helping to transfer information by implicitly pairing using a single seamless operation. So it's avoiding the use of all infrared transceivers, cameras, or identifier pen devices, which is actually making this application more useful. The ease of use is increased here. Also, it supports larger computing devices like the desktop PCs and laptops. So in the latest technology, we can see accelerators wherein the two mobile apps just need to tap or shake or something to establish the network connection and to transfer information. So here, in considering these large computing devices, all those options are ruled out. So what happens actually in the client application is, here the conventional dragging of an icon is performed after an object is selected, and after that when the user places the three fingers on top of that selected object, the stone image is appearing and the inter-device drag and drop process is getting activated. And similarly on the target device, suppose this is a target device, again when the user touches the screen, the image reappears, and the conventional dragging starts when the user removes all but one finger. Then the user can place the icon to the desired position using the conventional drag and drop option. So we can see here the operation is performed using more than two fingers. This is to avoid the conflict with other commonly adopted multi-touch two-finger operations like pinching, rotating, sliding, and tapping. So at the server side, the client collects all the information like timestamp, the global position of the computer, URL of the data object, the unique device ID, and fingertip positions. These are all data collected by the client and they are pushed to the server where the server preserves all this data. So in this picture we can see when a user touches the screen, the client is collecting all this information and is sending to the server. And when the user touches the target device, the server now starts to filtering those records based on the timestamp and the global location. And after that, it again filters the records based on the fingertip positions. After all these conditions are satisfied, the qualified records will be loaded into the target device. Once the application is completed the operation, the record will be deleted from the server. This is how the matching works. So when a record is received by the server and when it gets loaded into the and before getting loaded into the target device, the records that are physically the farthest from the destination device need to be removed. That's actually done using the co-location framework, wherein the location of the computer is analyzed and and the record is qualified based on the location of the source. So after that filtering, it will go to the matching of the fingertip shape. That's done using the polygonal congruence condition, wherein a record matching is done based on the fingertip shape. So once all these matches are confirmed and the qualified record is received at the target device, then the client application fetches the URL from the match record and loads it into the browser. Thus it completes the drag and drop operation. So we can see the URL fetch starts within 3 seconds after the user touches the destination device. So this can be seen as an area of improvement. This time can be actually improved, can be made a bit more faster. Then the threshold. First, when the user touches the target device, it calculates the distance between each pair of fingers and sorts them by length. Then it calculates the mean squared error between each pair. And finally, the system determines the fingertip positions are identical if the mean square error is less than the given threshold. So some threshold is set and the calculated value should be less than that for the fingerprint to be considered as valid. So how this threshold can be calculated? At what point the error cannot be zeroed out all the time, so we are keeping this threshold. So how can we calculate this? How is this threshold calculated? Let's see. So for calculating the threshold, we need FAR and FRR, false acceptance rate and false rejection rate. So for this, some 10 students were asked to perform drag and drop operation 40 times between two tablet pieces. And a graph is drawn out of those results. Like from this is the FAR and this is the FRR. So from this we need to calculate the threshold. The threshold should be such that it shouldn't be too low. In that case, even a correct user's finger will be rejected. And if the threshold is too high, in that case, an incorrect user fingerprint will be accepted. So to avoid that, the threshold need to be in between these two, like the FAR and FRR should be equal. In this graph, we can see it's at this point. It's like some 18%. So the threshold is set like this. After calculating FAR and FR, for this system, it's after this experiment is found to be 18%. Now some user evaluation experiments were performed, like one is to evaluate the effect of displaying the stone image, and the other one is to check the influence of an inclined touch surface. Let's see how it went. The stone image effect experiment. Here each participant were asked to perform drag and drop operation between two tablets, and each were given a question like how it worked while transferring the object with the stone image and without the image, like the visual feedback that we explained earlier. So, and the grading will be like 4 for strongly agree and 1 for strongly disagree. And the result was like 4 for with stone image and 2.6 without the stone image. And this showed that the stone image is relatively more intuitive than without a stone image. That was the result of this experiment. So the next is how does the inclined touch surface influence the technology? Like for the experiment on estimating the influence of an inclined touch surface, the participants were assigned data transfer tasks between iPad and an iPad that is tilted related to the horizontal surface. So we can see in this image here they are trying to transfer data from an iPad to a printer which is inclined. So the success rate was found to be 88 for 90-degree tilted and 92 for 45. So again, with this experiment, it was found that the memory stone can be applied to incline to a wall-mounted display, such as on a printer or a touch surface attached to a wall. The inclined surface is not at all affecting the performance of the memory stone technique. This is shoulder surfing experiment. That is, what if an information gets stolen by mimicking the formation of user's fingertip position? So here again, this students were asked to perform the drag and drop operation. Like there are two participants, participant 1 and participant 2. Participant 1 is performing some drag operation between some devices, and the participant 2 is standing behind him, some 30 centimeter behind, and he is asking to perform a copy and paste mimicking the fingerprint position of participant 1. So will that work? The success rate was found to be only 4. That means a person engaging in a successful shoulder surfing had to conduct a false paste operation within several seconds of the target user touch the transmitting device. So the threat of shoulder surfing is acceptably low in practical situations. So that also came out much like positively. This is the framework and how is that is supported. The prototype supports like is implemented for use on iOS 5 and Mac operating system. Then Windows 7 and 8 are also supporting it, as Windows 7 is having Windows Sensor Location, Windows 8 is having built-in position acquisition system. Then for the global location information, we are using the co-location framework supported by iOS and macOS. Then can be used in non-GPS equipped PCs also, as your OS will be supporting alternative position methods. Then it suppose a wide range of devices including smartphones, tablets, laptop, MacBook, then Macs, and then Macs desktop PCs. All these are supported by this memory stones. Then for improved performance, you can see the system should provide a lower FAR value than the result of this experiment by better use of this timestamp and location filtering. Then an improvement in FRR can be brought through by putting on a strict value on the threshold. Once the users get the master operation gestures, masters the operation gestures, then the threshold can be put to a bit more stricter value. So it provides a more secure operation. Then the problem here is like if there are a large number of people sitting in a meeting room or a classroom where there are a large number of people sitting in the same location, then the reliable data transfer can be seen to be difficult to achieve. Here, a very stricter judgment on the fingertip pattern similarity need to be analyzed. So that will be the difficult part, so some scalability needs at this point. So the conclusion is a novel user interface method executing drag and drop operation. It's of course a good interface which is helping the information transfer between smaller devices and between smaller and larger devices, between inclined surfaces. So it's actually a good interface method. Then also the experiment shows that it is proposed technique is positive. Then the shoulder surfing experiment shows that the technique is sufficiently secure for practical use. Like the success rate was only 4% when someone tried to mimic the finger position of the actual user. So only thing that is found to be need an enhancement is a scalability at the point where a large number of users are sitting in the same location and they're transferring information. At this point, the threshold is on a big question mark. Like at what point it should be, the rejection rate will be higher, or access rate will be higher. So that's a point where the real scalability is required. So this is the report that I tried to present here. Memory stones, and intuitive information transfer technique between multi-touch computers by Kari and Itero. Okay, thank you. Thanks for watching my presentation.